Euler's method and Heyn's method and three-term Taylor method and four-term Taylor method, which we didn't describe but works kind of similarly. It tackles first-order initial value problems where you have a first derivative. But if you write down any kind of a differential equation, pretty much straight away you're into second-order differential equations. Like even if you write down Newton's second law, you're talking about mass times acceleration, which is the second derivative of displacement. You're into equals sum of the forces. You're into second order with a second derivative. So we need to be able to handle this. So what are we looking at? So we've got something initially at rest. So let's write down something. V of 0 is equal to 0. And at a displacement plus a, so this is x of 0 equal to a. I see I've this written straight down below. Subject to a spring force, then if it's spring force, it's Hooke's law. The force is proportional to the displacement. It's in the opposite direction to the displacement, so it's proportional to minus displacement, and proportionality just means it's a constant times that negative displacement. So you get that the force is minus kx of t. So you end up with this second order differential equation. Now there's loads of ways of solving this. There's undetermined coefficients, Laplace transforms. You can even do this kind of fancy chain rule and solve for the speed as a function, or the velocity as a function of the displacement, and you can work from there. But we're going to do things slightly differently because, of course, in any kind of problem that we're looking at, realistically, we should be thinking that, oh, I actually can't solve it exactly. Now, sometimes I'll ask you to work with things you can solve exactly, but that's just because I want you to maybe see what the error is and see the effect if you reduce the step size or something like that. So what we're going to do is you're going to write something like this thing up here as two first order differential equations. And I'd actually never seen it myself until I taught this module. And I think it does actually give alternative ways of solving these using Laplace transforms. So if you've got a second order differential equation, like let me tell you what I'm getting at. So you have, say, y double dash of t. You do the Laplace transform, and what does it send it to? S squared times big Y of s minus s times y of 0 minus y dashed of 0. If you didn't know that, you could actually write your second order differential equation as two first orders and then solve it using methods that are used to solve systems of differential equations. Now, essentially, we're going to be doing that. Okay, so first of all, we need to, it works well in the applied example. It'll get a bit harder after that. We've got a relationship between displacement, velocity, and acceleration. So here's our displacement, x of t, no problem. If you differentiate, you get the velocity, otherwise known as dx dt. And if you differentiate again, you get the acceleration. So this is the derivative operator. The derivative or differentiate with respect to x operator. So we get to the acceleration. Now, we'll probably want to use that the acceleration is the derivative of the time, but in a question we'll see it as the second derivative. There's something I'm going to have to change there. I've called the displacement x. So the big ones we're going to be using here is that if you have a first derivative, you can let it equal to v. Now this, in applications, that's going to be a natural thing, but actually later on, when you have an abstract thing, you'll say let v be the first derivative. And then the second derivative is the derivative of the first derivative. Okay. Now that everything there should be 1,000,000% clear. So you've got a function x of t, you differentiate it, you can call the derivative v of t, it's the first derivative. You differentiate a second time, and it doesn't really matter what you call it now, but if you differentiate v of t, you get dv dt, and if v is the first derivative, differentiating v gives you the second derivative. Those two blue boxes are absolutely key. So So you can write out one initial value problem for v of t as the acceleration is the derivative of this. So if I look up above at this thing, I can write this spring thing as mass times the second derivative of displacement here is dv dt equal to minus k of x of t. And then what I can do now is I can make this an initial value problem. That's a derivative together with initial value for v. So remember, the way you kind of want to write them for Euler's method is derivative equals. So I just divide both sides by m. Now I like x of t, but I could leave this as x now. But look, I like x of t. And then this is the equation for v. So it should have the initial condition for v, which is given above. X dashed of 0 is 0. X dashed is the derivative of v. So v of 0 is 0. And then the second differential equation is very, very easy. So you've got a differential equation for v, and you also have a differential equation for x. But the derivative of x is just v. I'm going to write v of t. I probably should just write v. And then this is the differential equation for x. X of 0 is equal to a. Now doing this, writing the first order differential equation, the thing up at the top, as two first orders is absolutely vital, and students who cannot do this do not do well in this module. So you've got the basic programming for most of this module coming from your Euler method lab. If you're good at that, you should be okay at everything else. But to go further in terms of the theory, what you have to be able to do is probably be able to do this. And these two, the system of differential equations is equivalent to a single second order. Okay, so let us get some numbers going. I think we're going to do some calculations. Let me see what's happening on the next page. Yeah, so let's do some calculations. So what have we got? We're going to do a step size of 0.01 and off we go. So we'll do v first. Actually, is it more interesting to do x? It doesn't actually matter. Okay, so, and it's going to be a comment here for VBA comment. Yeah, so let's do the next x value. So the next x value, which is what's happening at 0.01, it's approximately, so now we're actually going to use Euler's method. Now, obviously you can extend and do Heyn's method or three-term Taylor at this. So x1 is the previous x value. What's the previous x value? It's written here is 0.2. Plus the step size is 0.01 times the previous slope. And the slope of x is v. And what's the previous v? 0. So I get 0.2. What about the velocity at the next point? This is approximated by what we're calling v1, which is the previous velocity, which is 0, plus the step size is 0.01, times the derivative of the velocity. The derivative of the velocity is minus 4x. Minus 4x. Now remember, Euler's method says the next value is the previous value plus the step size times the previous slope. Previous slope. What's the previous x value here? I mean, I like what I'm saying is that we're looking at v and the derivative of v depends on x. What's the previous x value? It's not 0.2. We'll draw a picture down below before we do our VBA note. The previous x value, well actually it is 0.2, but it's not this one, it's this one. And so I'll go into the calculator. I shouldn't really have to. Is it 0.8, 0.008 or something? Minus. A bit tired. I should really have been able to do that. 0.008. Okay. Now I'll just calculate two more and then we'll make our VBA comments. So the next x value is approximated by what I call x2 is equal to the previous x value, which is 0.2, plus the step size, which is 0.01, times the previous slope of x. The slope of x is v, so the previous v is minus 0.008. Bang this into the calculator, what do we get? 0.2 plus 0.01 by minus 0.008. Tiny number. It's looking like minus 0.123416. I think that's what I get anyway. That's not right. Apologies. It is 0.19. That didn't make any sense, did it? 992. And now we do v of 0.2 is approximately v2 is equal to the previous v value, which is minus 0.008, plus the step size is 0.01, and the derivative of v is minus 4x, and the previous x is 0.2. So minus 0.008 plus 0.01 times minus 0.8. And that's minus 0.088. So now, important point. In VBA, so when you get to, so we'll do it, say, here. So at star, use previous x. In this case, x1. Now the thing is, if you write out these things, so this kind of stuff in VBA, you're tempted to write something. Now I'm not going to put in the DBLs, but you're tempted to write v is equal to v plus step size times the derivative of v is minus 4x. And then you're tempted to write x is equal to the previous x plus the step size times the slope of v. Now if you write it in this order, when this line is executed, the value of v that is now being stored will be the new value of v. It won't be the previous one. So you've got two options, okay? So the fix to this problem in VBA is you use now it can be either x old or v, so you use old variables. Now this will go into the thing, or printed values. I will reference this, I think, in the lab videos, but it's just something to, although I don't think it's relevant until it's not ever its lab, it's the one after Heyn's method. Okay, but it is something to look for. Obviously, we are not going to continue doing this all day, so we use a computer and we end up with something like this. So this used about 1700 steps. Can we see a problem with the approximation? Now this is a spring, and there's nothing but a spring force, and look at the energy has been increased. Look at this is the amplitude is increasing. Now, just a small kind of comment. In general, the systems you study, you won't see energy added to the system. So a comment in terms of code in VBA, usually, so energy increasing. So if energy is going to infinity, it usually means in VBA there's a sign error. Now this isn't a sign error because this is Euler's method. It's not very accurate. And so the errors are compounding, and what this will get bigger and bigger and bigger and bigger. So if you go to Heyn, you'll do a bit better. Are we going to do Heyn? Oh, that's fairly painful, but we'll do it. Okay. So let's write down our thing again. So we had dv dt, the derivative of v was equal to minus 4x, and I'll leave out the t now, together with the initial value of v was it 0? Yeah. And the equation for x, dx dt is equal to v, and the initial value of x is 0.2. Okay, so let's do Heyn's method here. Right, so we need to get two predictors, and I think we'll do that. Okay, so v1, now I won't be writing down what these are approximating. It's kind of obvious because we're going in steps of 0.01. So v1 predictor is equal to the previous v value, which is 0, plus the step size, which is 0.01, times the previous slope, which is minus 4 times x. The previous x I get over here is 0.2. And, oh yeah, you actually have to calculate both predictors here. Yeah. And this is equal to, I really should be able to do this in my head. 0.08, does that sound right? It does, doesn't it? Yeah. Now, we should also find the x predictor. So the x predictor says that the next x value is the previous x value plus the step size times the previous slope, which is the previous v, which is 0. So I get 0.2. You see, I think I want these because this is actually, now it doesn't change, so yeah, but this is actually going to feed in over on the left-hand side, and this is going to feed in over on the right-hand side. So that's why I needed that. Now, hopefully space is going to be okay. So the next v value, according to Heyn, now what's Heyn going to do? For a start, it's going to take the previous v value, which is 0, plus the step size, but now it's going to average two slopes. It's going to average the slopes, the previous slope and the predicted next slope. So what is the slope of v? It's minus 4x. What's the previous x value? 0.2. So it's doing minus 4 times 0.2. So that's the slope at the previous point. Now, what about Euler says is the next point? Euler says that the next x value is also 0.2. So actually, we're not going to get any change here. So this is also going to be minus 0.008. I'll probably do a few iterations of this, maybe two. Right, what about the x1 Heyn? And as well, you could, if you wanted, if you're kind of keeping an eye on second derivatives, maybe if one of the second derivatives are small, you could probably get away with maybe doing Euler with one and Heyn with the other. We'll do Heyn with both. So x1 is the previous x value, which is 0.2, plus the step size is 0.01, and now the average the two slopes. Now, what's the slope of x is v, so the previous v value is 0, plus the predicted next v value is over there on the left, underlined in yellow, minus 0.008. And this is different to what the Euler method said. So we're getting 0.2 plus 0.0, oh, I forgot to divide by 2, plus 0.01 times minus 0.008 divided by 2. So I end up with 0.19996. Is that different to what we had with Euler's method? Yes. So we had 0.2, and now we've got a more accurate picture. Okay. Now we'll do another iteration. Now we will see these values in a table on the next page. So here's our Euler predictors, and then our Heyn's. This is also an Euler predictor. So we'll do it again. Now you might be a bit lost here, so maybe I'll put down some coordinates. So the coordinate here is 0.01. The problem is what are our coordinates? Our coordinates are actually three-dimensional because there's a t, an x, and a v. So let's write down t, x, v. So at the moment the t value is 0.01. At the moment the x value is 0.19996. And at the moment our best guess for the velocity is 0.008. Yeah, we're just going to do one more iteration of this. Okay, So let's figure out what's going on at the next point, point 02. So we'll do our predictors first. So our v20 for what's going on at point x equal to point t equal to 0.02 is the previous v value. Now the previous v value is this, minus 0.008, plus the step size is 0.01 times the slope of v. The slope of v is minus 4 times x, but now the previous x is the 0.1996, which is better than the last time. So we get for the v predictor here, minus 0.008 plus 0.01 times minus 4 by 0.19996. It's coming out as, I do appreciate this is very tedious. It's very tedious for me too, 9984. Okay. We should also calculate the Euler predictor for x. So it says the previous x value, which is this 0.19996, plus step size is 0.01, and then the slope of x is v. So it should be the previous v, which is this minus 0.008. And this is equal to 0.1996 plus 0.01 times minus 0.008. And I'm getting 0.19988. Okay, now let's do Heyn's method. So Heyn here says v2 is the previous v value. Now the previous v value is in blue. It's the minus 0.008 plus step size, which is 0.01, and then average two slopes. The slope at the previous point, which is the point in blue. Now we have to think, what is the derivative of v? It's minus 4x, so it'll be minus 4.19996 plus the slope at the predicted next x value. Let's underline that. Well, it's the slope of v is minus 4x, and this is where we predict we're going to be, so it should be minus 4 times that. Sure, we'll keep the color. Now I'm running out of space, so I'm going to do 0.19988, and we'll bang that into the calculator. See what we get. So minus point, I'm just going to pause and do it like that. And it comes out as minus 0.015998, which is going to be slightly more accurate than the predictor above. And we go for x2. So x2 equal to the previous x value, which is in blue, 0.1996, plus step size is 0.01, and then we average two slopes. Now the slope of x above is just v. So we've got the slope according to the blue point, which is just minus 0.008, and then also the slope according to the v predictor, which is this minus. I'm just going to write in a few significant figures, but I'm actually going to write I'm going to use more in my calculation. Now you can see already that they're like, even with Excel, you're going to have rounding error, and so things aren't going to be perfect in there. You're going to get additional rounding error, and there's obviously a small mistake here because this has got 3 nines. Very tedious, isn't it? And I hope I'm not making a mistake. Can't stop making mistakes. That should be 0.01 over 2, then the two slopes minus 0.008 minus the green thing 0.159984, and I get 0.19984, then kind of doing the dog on it. Usually in the exam I just ask for 5 significant figures or something. Now hopefully we see these numbers in the next page. We're not going to keep doing this all day. Yeah, we can see some of them. Look, there's the number we were talking about. Let's go back and just see the predictor. the minus 0.016 predictor in green. Is there. Yeah, they're all there. The 996 is there, etc. Now look at what's happening now. We don't seem to be getting the big errors. This use about, can we see specific improvement yet? Yeah, you're not getting the energy being increased, so that's good. Now this method, you can write a third order as 3 first orders, and the first order is 4 first orders, but we're only going to be seeing second order derivatives. Now, usually when it's a concrete problem, so an applied problem, it's easy to see what to do. Let V be the derivative of displacement, but in abstract problems, it's a bit more difficult. So you just have to be proactive enough to say, okay, let V be the first derivative. In this case, dy dx. And then what you can do is you can differentiate both of these with respect to x. So you get dv dx is equal to the second derivative of y with respect to x. And you have to be able to do that. So you can do, the first thing might be like, okay, let's first of all maybe just rewrite this thing, take our time here, because I think we're going to have the system of ODEs down below. So the second derivative of y with respect to x is the same as dv dx. Plus, I'm just going to write as 6y equal to cos of x. And then I can get an equation for v by taking 6y away from both sides. So dv dx is equal to cos x minus 6y. Okay, so we've got two equations, one for v and one for y. Let's do the equation for v first. So dv dx is equal to cos x minus 6y. And that should come together. It's an initial value problem. What's the initial value of v? Now v is the derivative of y. And if you look above, we have y dashed of 0 equal to minus 2. So v of 0 is equal to minus 2. And then the other one is the equation for y, dy dx. And you see it's a bit harder. Because alternatively, you're looking at dv dt or something. Or is it even be dx dt? And you know that's v. And this should come with the initial value of y, which is 1 taken from the thing above. Okay, so I think we're going to have a bash off this. So as I said before, we need to find both of the predictors. That has probably implications. If you're doing this in a lab, you'll need to calculate the predictors before you do the Heyn. So there's a y and a v. So you'll have to do the predictor for y, then the predictor for v, then the Heyn for y, then the Heyn for v. You won't be able to do predictor y, Heyn y, predictor v, Heyn v. You won't be able to do it in that order. Okay, so starting at this point, let's find the predictors. So y1, 0 is the previous y value. I'm getting it just from here is 1. The step size, I think, must be 0.1. Yeah. Because we're going to do 2 iterations, we're going to get to 0.2. So this is plus 0.1 times the slope of y, I have it written on the previous page, is v. And the previous v is minus 2. Okay, so the y0 predictor is 1 minus 0.2, which is 0.8. Let's do the predictor for v. v1 predictor is the previous v value, which is in the brackets there is minus 2, plus the step size is 0.1, and then the slope of v is cos x minus 6y. Now remember, any differentiation you have to use radians. So it'll be cos of 0 degrees, well, that doesn't make any difference, minus 6 times y, and the previous y was 1. Now I'm just going to kind of cheat. I'm just going to look at the answer down below. I know this is going to be minus 2.5. Now let's do Heyn's method. So Heyn's method says for y1, it will be equal to the previous y value. So the previous y value is back up the top in the bracket is 1, plus the step size is 0.1. And then the slope of y on the previous page is v. So we need to average two slopes. V at the previous point, which is -2, and V at the Euler predicted next point, which we calculated in the right-hand corner here. So what's predicted to happen at the next, look, here it is. So this is the Euler predicted next point. So this is the current point and the Euler predicted next point. And when we're calculating slopes, we average one from here, one from here. So the derivative of y is just v. So the first derivative is -2, and the second one is -2.5. And here I'm just going to cheat. I'm just going to look down below. I know we're going to get 0.775. Okay, and look, to kind of get with Heyn's method more precise. Now that doesn't mean accurate, but it is more accurate. Look, 0.8 versus 0.775, one significant figure versus 3. Now let's also do V1 using Heyn. So the next V value is the previous V value. So the previous V value to V1 is V0, which is just -2, plus the step size, which is 0.1. And then we look at the slope of V. I have not given enough space here. So the slope of V is cos x minus 6y. So it's going to be cos of x. What's the previous x? 0. Minus 6y. What's the previous y? 1. Plus the Euler predicted next slope. So cos x, what's the next x? It's written here. 0.1 minus 6 times the predicted next y value is 0.8. Really should have given myself more space there. And then just cheating, I'm just looking down below and I'm not sure. The rounding figure here suggests that there is rounding in this. Oh, sure, look, cos of 0.1, there's definitely rounding. Minus 2.44025. So that's one iteration of Heyn's. Let's keep going, we can do it. So we go again. So the y2 predictor is the previous y value, that is in this bracket in here, 0.775, plus the step size, which is 0.1, times the slope of y, and I really should have given myself more space, sorry. So y2 predictor, previous y value is 0.775, plus step size is 0.1, slope of y, previous page is v, previous v is this minus 2.44. Now I'm not going to write the rest of it, and I know we're into rounding territory anyway, and just from looking down below, I know that this is approximately 0.530975. Okay, and then the v predictor is equal to the previous v value is in this bracket, the minus 2.44. Now I'm only going to write that, but in the calculation I'm going to use more of it. Plus 0.1 times the previous slope. Now the slope of v is cos of x. Now at this point, when we're going to, so we started at x equal to 0, then we went to x equal to 0.1, and now we're looking to 0.2. So the previous x, or kind of previous slash current, is 0.1 minus 6 times y, which is this 0.775. And now this is approximately minus 2.80575. And now one more, we can do it. This will finish the, we'll look at the table, we'll finish what we're doing. Yeah. So y2 is equal to the previous y value. So look at the 2 points we're looking at, previous slash current, and Euler predicted next, and we're going to combine those two. So next y value is previous y value, previous slash current, 0.775. I'll have to go into the calculator for this, plus step size is 0.1, and the slope of y, well, we're going to average two slopes. The slope of y is v, so we're going to average the previous v, which is this minus 2.44, but I will use more precision than that. I'll use 6 significant figures, plus the predicted, Euler predicted next one is the minus 2.81 in the second point, divided by 2, and this I will use better precision, but I will pause the lecture to do it. And this comes out to be 6 significant figure. Oh, it comes out kind of nice. 5127. Now, yeah, let's just leave it as it is. And then how about V2? So V2 is the previous V value, which is this minus 2.44, plus step size is 0.1, and now average two slopes. Now both of the slopes are of the form cos x minus 6y. So cos of something minus 6y. And the other one is also cos of something minus 6y. So this is using the previous x value. So now when we look at the table, maybe some of this will be explained better. This is 0.1 and the next x value is 0.2. Now we can look at the two, and look there, actually they're both in the two yellow underlined. Previous was x equal to 0.1, next is 0.2. And then do it with the y's. So the previous y value looks like the 0.775, and the predicted next one is this 0.531. I'll pause again. And this comes out to be minus 2.73. 3. We'll go for 4 significant figures as well. Okay. Now there's loads of rounding errors here. Let's put this in the table just so we can understand what happened kind of globally. I won't put in the, or maybe I will put in the predictors as well. So we have x, y, v, and the two predictors can go on here. So let's go with x, y. Now that's the Heyn, v, Euler Predictor, v. Okay, so we went from x equal to 0 to 0.1 to 0.2. We had initial values of y and v of 1 and minus 2. These are initially undefined. Okay, so what we calculated first was the two predictors, 0.8 and minus 2.5. I'll probably only use two significant figures here. Then we improved it using Heyn. We found 0.775, which is 0.78, the two significant figures, and minus 2.4. Then we found two more predictors. For y, we found 0.53. And for v, we found minus 2.81. And we improved on them with the Heyns, which were 0.51 and minus 2.7. Okay.